I'm Chris Forbes, and I am a member of ARCS. And I had the honor, I guess, of being the first, finding the first presenter for this year's Science Activities Committee. And I would like to welcome everybody and thank you all for joining us this evening. It's my great pleasure to introduce our first science activity speaker of the 2022-2023 academic year, Dr. Raja Guha Thakurta, Professor, Astronomer, and Department Chair of the Department of Astronomy and Astrophysics at the University of California at Santa Cruz for nearly 3 decades. Some of you attending tonight's talk may recall that Raja was, which is what he most often goes by to help us with the pronunciation of his last name, was one of our moderators at our 2022 ARC Symposium event, and one of the most popular, I think, moderators and focus groups. And we're very fortunate to have Raja join us again tonight. He's extremely generous with his time to ARCS and is a big supporter. So thank you very much, Raja. But before I turn this over to Raja, I'd like to give you a little bit more background about Raja. Raja received his master's and PhD in astrophysics, physical sciences at Princeton University, and his BS in science in physics at Xavier's College in Calcutta, India. Before coming to UCSC, Raja performed research at the Institute for Advanced Study in Princeton University, and the Space Telescope Institute in Baltimore, Maryland. His main research topic is galaxies, how they form and evolve into the dramatic structures we see today. Of course, we have to see them with the telescopes, I'm sure. Raja is also part of a research group that studies chemical enrichment and star formation history of the galaxies using, among others, the 10-meter Keck telescopes, the Subaru telescope, the Canada, France, Hawaii telescope on the summit of Mount Mauna Kea, and the Big Island of Hawaii, the Lick Observatory telescopes on Mount Hamilton, and the Earth orbiting Hubble Space Telescope and the James Webb Space Telescope, all of which are among the most advanced instruments in the world for celestial studies. He's playing with some very expensive hardware there. Now, one of the unique attributes of the research group is that it includes young people, high school students, undergraduates, graduates, and postgraduate students. Raja and some of his UCSC colleagues also run the Creating Equity in STEAM umbrella of programs, including the Science Internship Program, or SIP, for high school students, and the Shadow the Scientist, STS program that allows students, educators, and other interested parties to eavesdrop on scientists doing science in real time. I think that's a pretty exciting concept for all of us lay people. While not teaching, conducting research, and mentoring, Raja in his free time creates art. His love of art started with his family of artists, of whom his mother, sister, and especially his maternal grandmother served as a tremendous source of inspiration for him to pursue this passion. Raja is an accomplished artist, most often working in pencil and oils to create detailed, realistic portraits of animals and people. He also dabbles in wood carving and ceramics and has shown his work in many venues in the Bay Area and in statewide competition. Raja told me that growing up, his plan A was to become a professional artist, and being a scientist was plan B. While plan A was sidetracked, plan B was activated as Raja's studies, augmented by trips to the planetarium in Calcutta, exposed him to the night skies, which they couldn't see because of the pollution. Watching David Attenborough's Life on Earth, a British television natural history series in high school, sealed the deal, compelling him to explore the mysteries and awaiting the discoveries the universe holds. To that point, Raja's presentation this evening will touch upon the highlights from the group's research on galaxies, and in particular, their ongoing research in the outer regions of the galaxies we live in, our Milky Way galaxy. He will also talk about the properties of the resolved population of stars that make up these galaxies, tell us a lot about the formation and the complex evolution history of the galaxies. Raja will also inform us about how the motion of the stars tell us about the dark matter content of galaxies and their cannibalism history. I find that word very interesting in terms of context of the universe. All of this will be illustrated by some of the latest images from the James Webb Space Telescope, the Hubble Space Telescope, and those ground-based telescopes. Raja, the sky is yours.
Thank you so much, Chris. Is it okay to share my slides now?
Yes, you have complete control. I think Nancy's giving you control. And I would just ask everybody else to mute, if you don't mind. And then I should say at the end, we are going to have a question and answer period, and then one little sort of surprise sharing.
Thank you. Okay, you should be able to see my slides now. And
Yes.
I will go to my very first slide and take it away from there. Okay, is my audio okay?
Yes.
Oh, fantastic. Thank you. So, Chris, that was such a kind introduction. I'm very, very grateful to you for such a kind introduction. I will speak about the following topics. I'll talk about the universe of galaxies, and specifically the research that my collaborators and I have done over the years, how they relate to the James Webb Space Telescope, some of the latest images from that telescope, and how this is intimately linked to the participation of young people and how we're using this to build greater equity in STEAM, in science, technology, engineering, art, and math. I have been a professor at UC Santa Cruz for nearly 3 decades. Thankfully, I've only been department chair for the last 3 years. It would have killed me if I'd been department chair for 3 decades. And some of the outreach work I do was really fostered and helped by Google, the company Google, because I spent a sabbatical at Google headquarters in Mountain View 7 years ago. I spent the better part of a year there. And fittingly, my very first content slide after this one, this picture in the background are pictures of distant galaxies. I'll say more about those galaxies in a minute. But my very next slide is a picture of the galaxy we live in, and it's taken by one of the Zoom participants. I was very happy to see John Rockman on this Zoom call, and John kindly lent me not this single slide, but this is a movie, a time lapse, if you like, that he took of the Milky Way. Again, John Rockman is at the Castlear School, Palo Alto, and he kindly lent me this movie clip. So I'm going to remove the title so you can focus on the video itself. And you see this sort of hazy band, nearly horizontal band close to the horizon, is our home galaxy, the Milky Way. But in this time lapse, you can see how the Milky Way appears to sweep across our sky. And you can see shooting stars and lightning and clouds and a tree fluttering in the breeze until someone turns the light off. And the Milky Way continues to appear to sweep across the sky. And this is, of course, because of the rotation of the Earth. And this band of light and darkness, the band of light is produced by stars, and the dark clouds obscure some of that light. So that's what we call our home galaxy, the Milky Way. But what I want to share with you next is a different time lapse, this time put together by a different astrophotographer, Arya Narenberg. And what Arya did was, instead of keeping the camera fixed, he kept the camera trained on the Milky Way so that the Milky Way remained fixed in orientation on his digital camera. So I'm going to remove the label and you'll see what that does. So when you keep the camera trained on the Milky Way, it means you have to physically rotate the camera to compensate for the apparent rotation of the sky. And when you do that, you can't help noticing that we live on a planet that is spinning. You can see the rotation of the Earth quite literally relative to the Milky Way in this movie clip from Arya Narenberg. So again, these are views of our home galaxy, the Milky Way. And And you can even see planes flying across close to sunset or after sunset. You can see the electrical wires. This is a beautiful video that there's a plane going across, couple of planes going across. And now, of course, the rotation of the Earth is such that the Milky Way has set, so you can't see it anymore. Okay, here's another view of the Milky Way. Again, it looks more or less vertical in this frame. And if you're a fan of the night sky, you might notice that there's sort of a diamond pattern. If you can see my cursor, there's a diamond pattern. This is the Southern Cross. And it's not far from where the southern axis of the Earth, the rotation axis of the geographical South Pole, points to the counterpart of the pole star in the north, the southern pole, south celestial pole. And what is highlighted here in this red square is a nebula, a cloud of gas and dust. These nebula are where new stars are born. This is taken by an astrophotographer, Faber. And I'm going to zoom in next to just that red square. Okay. So in the next slide, I'm going to go back and forth once. So you see the red square there in the lower part of just above the tree. And here you could only see the contents of that red square. And this is a different astrophotographer, Harold Boren. And in this view of the Carina Nebula, you can see in the upper right what looks like a little cloud-like structure. So in the next zoom, you can see that cloud-like structure is in a red square. We're going to zoom into that red square. And when you do, this is what we see. Now, these are all images taken from the ground. This last image here that you're seeing is taken from a very famous telescope, the European Southern Observatory Telescope in Chile. Now, this is a cloud of gas and dust. And if you look closely at this red rectangle, you'll notice that there's some kind of edge here with a little finger pointing out. So I'm next going to show you the contents of this. I'm going to zoom in to show you only what is inside this rectangle, but I'm going to rotate the rectangle so it's horizontal. So again, the contents of the rectangle are shown here. I'm going to go back and forth. And the way to find an anchor point is to see this little finger here with three or what looks like a mini Southern Cross above it. Okay, so that's this little finger with the mini Southern Cross above it. And what you're seeing now is a comparison. The top image is taken from that telescope in Chile. The middle image is taken with the Hubble Space Telescope. And the lowest image is taken with the James Webb Telescope. And the contrast between the James Webb Telescope and the Hubble telescope image is striking. Just look at the number of stars, number of faint stars that are visible in the lowest image compared to the middle image or the top image. Okay. First of all, the stars in the top image look really blobby because of the effects of the Earth's atmosphere causing the stars to twinkle and blur them out. You don't see that much blurring in the Hubble image, but you can see very faint stars in the James Webb image. Next, we're going to zoom into this little segment that contains this little thumb. Now, this thumb is bigger than our solar system, just to give you a sense of scale. This thumb is, in fact, a forming system of planets around a star. So it's a vicarious view of what our own solar system may have looked like prior to it breaking up into planets and a central star. So if we zoom in, you see, again, the thumb is sort of blurry in the ground-based image, even though this is one of the best ground-based telescopes. In Hubble, you see it more clearly. And I'm blown away by the James Webb image, where you see so many stars in the night sky, just because of its greater sensitivity and its ability to peer through the infrared, through dust using infrared light. Okay. Again, this little thumb is a forming solar system that in its current size is much, much bigger than our current solar system of planets. Okay, I want to switch gears a little bit, and I want to show you this star field. And this star field is not a static image, it's also a time lapse. And if you look closely, you'll notice that certain stars, I'm going to put my cursor next to one of these stars, you'll notice the star is pulsing in brightness. This is not the only one that's doing it. The star to the left is doing it, star to its left, the star to its lower right is doing the same. And in fact, now that you know that stars are some of the stars are pulsing. You can find many of these pulsing stars. Here's one. You'll notice something special about the pulsing stars. They all look sort of bluish white in color, and they all look like they have about the same brightness. That means at their brightest point, they're all about the same. At their faintest point, they're all about the same. Their average brightness as they pulse is about the same, but they're not pulsing in sequence. When one gets brighter, another one could be getting fainter. These are real pulsing stars. It's a time lapse, and these pulsing stars have a wholly unromantic name called RR Lyrae. They're named after the prototype of such stars. And it's in a cluster of stars, again, with an entirely unromantic name of M3, Messier 3. And what's special about these stars is these are great, what's the word for it? These are great markers for us to find distant stars in our own galaxy, the Milky Way. You know, you saw the previous pictures of the Milky Way where we're zooming into the nebula of gas and dust. That's at the heart of the Milky Way. If we look in the outskirts of the Milky Way, these marker are our Lyrae stars. They're not just present in star clusters, they're present throughout our galaxy. They become really important. And I want to show you a little cartoon to show you some of our current work, ongoing work, unpublished paper about to be published later this month, of studies of RR Lyrae in our Milky Way. Okay, so this is now an artist's impression of a Milky Way. We've never taken pictures like this of our own Milky Way. You know, John's picture of the Milky Way, Arya's picture of the Milky Way are about the best we can do. We'd have to have a very long selfie stick to take a picture of the Milky Way like this, and we don't have such long selfie sticks because, you know, if the sun were shown on this map, the sun would be smaller than a pixel, so I'm not showing it to scale using this symbol, but the distance between the sun and the center of our galaxy is 25,000 light years. So we need a selfie stick that's longer than that to take a picture, an external picture of our Now, what I'm going to do is remove these labels, turn the Milky Way, this is an artist's impression of the Milky Way, turn it on its side, so you're seeing it edge on. I'm going to shrink it so I can show you the positions and distances of the stars that my students and I have found in the Milky Way, these same RR Lyrae stars that I showed you that time lapse of. Now, again, to scale, every dot is an RR Lyrae star found in this sort of triangular wedge. Now, if the diameter of our galaxy is about 100,000 light years, you know, the bright part of our galaxy, these stars are located 10 times further away, million light years in radius from the center of our Milky Way. So about 40 times the distance of the solar system from the center of the Milky Way. So this is redefining how big our Milky Way galaxy is. Now, this is the work of my PhD student, Yuting Feng, and my former PhD student, Emily Cunningham. We're still working together. In fact, tomorrow morning, I set out for Hawaii, and we'll be making measurements of some of these stars later this fall. Now, I want to switch to a different galaxy, the Andromeda galaxy. This is my favorite galaxy in the whole world. And this is not a single image. It's 4 versions of the same image. It's 4 different contrast level, but each and every one of the, you know, if you pick a contrast level, each and every one of these is a composite, a digital composite of 57 images, some in blue light, some in infrared light. You see the low contrast image on the far left, the high contrast image on the far right. And, you know, this is a satellite galaxy of Andromeda, this small galaxy here that I'm putting my cursor around. We're about to make measurements of this later this month. That's one of the reasons I'm going out to Hawaii. And you see another galaxy peeking out from the left here. And this image was put together, when it was put together, it was the first digital mosaic. You know, people had taken individual digital images of Andromeda, but it was the first digital mosaic. And it was put together by 2 of my students. The stitching of the mosaic was done by Andreas Berlind, who was an undergraduate at the time, and later Phil Choi, who was a grad student at UC Santa Cruz. Andreas was an undergraduate at Princeton. And Shomak Rai Chaudhary, my collaborator, and I, we collected the raw images from a telescope in Arizona on Keck II. Now, if we fast forward, this is a modern digital image, not a mosaic, a single image taken by Robert Gendler, who's an astrophotographer. And the telescope I'm going to use when I go to Hawaii Those two telescopes are gradually coming into view during a Mauna Kea sunset photographed by Laurie Hatch. It's the Keck I and Keck II telescopes, some of the most powerful telescopes on the ground, right? They're on the summit of Mauna Kea, sacred summit of Mauna Kea, 14,000 feet above sea level. And we astronomers are super privileged to use a telescope like this that is sitting on land that is of great significance to the Hawaiian culture, to the Hawaiian people. And one of the things we're doing with this telescope is when we observe with it, as Chris mentioned, and as I'll highlight a little bit later, is we make the observations of the telescope, the actual observing sessions, we open them up via Zoom to children and educators around the world. So a lot of Hawaiian students take part. We have students from Africa, Central America, students from Asia, Europe. We have students from Kosovo taking part in these observations. And it's a wonderful way to connect a community of young people, inquisitive young people, to some of the world's most powerful telescopes. Now, I love this image that was posted recently. This is a James Webb telescope image, space telescope image of something called WLM. Astronomers are terrible at coming up with names. WLM is a small galaxy orbiting the Milky Way. And in this planetarium view of the James Webb view of WLM, the participants in the planetarium, their comment was, looking at this planetarium screen, we thought we were inside this galaxy.
Okay, honey.
It's really spectacular. It's this all-encompassing thing. I can't imagine looking at something like this, all over a planetarium dome. I want to show you some images, not just from James Webb, but also from the Hubble Space Telescope. And this is a survey we did a few years ago. It was led by Julianne Del Canton. She was then at the University of Washington. It's called the Panchromatic Hubble Andromeda Treasury. I talked about how my students and I first put together a digital mosaic. That was 30 years ago. It was in 1992, and it was a measly 57 images. What Julianne, the team led by Julianne, our team, the mosaic we put together had 3,000 images. Not 57, 3,000. And these images were taken not from the ground, but with the Hubble Space Telescope. And they cover a region of the Andromeda Galaxy that's sort of shown by this crime scene chalk outline here on the left. And this is Andromeda. This is the full moon to scale in terms of its apparent angular size on the sky. So the Andromeda is very big on the sky, but it's very low contrast, so it's hard to see. And so over 4 years, across 828 orbits of Hubble around the Earth, Hubble takes an hour and a half to complete an orbit. Across 828 orbits spread out over 4 years, we took images of Andromeda in 6 filters, in 2 ultraviolet filters, 2 visible light filters, and 2 near-infrared filters. And I'm about to show you the details of the Hubble mosaic. We're going to zoom into this Hubble mosaic. And in this, before we zoom in, what you see is the arc of the Milky Way, this giant arc of brightness and darkness. These are clouds of gas and dust interspersed with with a dense collection of stars in the Milky Way. And as we zoom in, we're going to zoom into the Andromeda Galaxy that's 2.5 million light years away. Light takes 2.5 million years to travel from the Andromeda Galaxy to us. We just zoomed past 2 of its smaller orbiting galaxies, satellite galaxies. But as we zoom in, this is not an artist's conception. This is an actual Hubble Space Telescope image where you feel like you're inside the galaxy because you can see individual stars. They have different colors. The lowest temperature stars look red in color. The highest temperature stars look blue or bluish white in color. I'm avoiding saying coolest and hottest because, after all, the sun is the coolest star in the universe, and it's also the hottest star in the universe. But in a temperature sense, the red stars here are some of the lowest temperature stars in Andromeda, and the blue stars are some of the highest temperature stars in Andromeda. A sun-like star in this image would look sort of a yellowish white. And you see these dark patches of gas and dust. And this is similar to the dark patches of gas and dust that we see in the Milky Way that I had zoomed into earlier using James Webb images. Now, one of the things we've done with this image is we've identified stars for which we want to make further measurements with the James Webb Telescope. So in this rectangular region called B19, stands for brick 19, PHAT was the panchromatic Hubble Andromeda treasury. In brick 19, this rectangle, we're going to take the stars here, and this plot on the right here shows you the brightness of the star on the y-axis. So brighter stars are in the upper part of the diagram, fainter stars in the lower part of the diagram. And the x-axis of this graph is showing temperature. The cooler stars, lower temperature stars, are on the right, numbers like 1.5 and 2. And the higher temperature stars show numbers like minus 0.5, 0, or 0.5. So it's an inverted scale that's related to temperature. So temperature increases from the right to the left, and brightness, how luminous the star is, increases from the bottom to the top. Again, that's an inverted scale. You see the number 24 is at the bottom, number 16 is at the top. So astronomers use an inverted scale of magnitudes. So both of these scales are reversed. Temperature, again, temperature increasing to the left, brightness increasing upward. And what we're going to do with some of these stars, the ones that are shown enclosed in this sort of parallelogram here, actually a trapezium here, we're going to measure spectra of stars. And you're seeing model spectra, because we haven't taken these spectra with James Webb yet, but when we take James Webb spectra, they'll look something like this. And you'll notice that there are 4 spectra, red and black here, red and black here. And you'll notice that this dip in particular at 1.1 is very, very mild in the lower spectra and much more significant in the upper spectrum. And what's different between the spectra is they have the same temperature of about 4,000 Kelvin, but they have different ion abundance. So the ratio of iron to hydrogen is similar to the sun in the upper one, and it's 10 times more anemic than the sun for the lower models. And the difference between red and black has to do with the chemical composition of other elements like calcium, sodium, potassium, relative to iron. So we expect to take these spectra of stars using James Webb next year in order to understand the chemical composition of stars in the Andromeda galaxy. And in a moment, I'll explain why chemical composition is important, even in a galaxy like Andromeda or the Milky Way. Okay. This quite literally is the pattern of metal plates that will cover the focal plane of the telescope, of the Keck telescope, when we go to work next week. That's why I'm flying out to Hawaii tomorrow morning. And in particular, this mauve pattern that looks like a Japanese fan is going to target the small galaxy in Andromeda, and we're going to measure spectra of individual stars. You can see some of these stars in this image, but most of the stars for which we'll get spectra are too faint to be seen as individual dots in these images. So this is a map and a real plan of what we're going to observe next week. This is literally upcoming. These particular observations, some of them will take place next week, but most of them will take place on the 26th and 27th of September. So not this coming Monday and Tuesday, but the following Monday and Tuesday. And when we do that, you're all welcome to join a Zoom session and watch what we do with the world's most powerful telescope and spectrograph, and you'll be accompanied by children and educators around the world. And I'm happy to send information about this to Chris and others. Chris, you may have already received some of the Chat of the Scientists information for this week, but if not, I'm happy to send it out. Okay, how am I doing on time? Please give me a time check, since I'm not looking at my clock right now.
You're doing fine. Oops.
Go ahead. Would you say I have another 10 minutes?
Oh, absolutely. Go for it.
Okay. Okay, so what I'm going to talk about next is galaxy cannibalism. Chris raised an eyebrow when I said galaxy collisions and cannibalism. When galaxies gobble up smaller galaxies, they're like corporate mergers. It's like a big company swallowing a smaller company. Nothing happens to the people. They just switch loyalties. Instead of working for the smaller company, now they work for the bigger company. Galaxy collisions take a long time. They take billions of years. So we can't see it happen in any one actual collision. What we can do is speed up time in computer simulations, and we can string together different pairs of galaxies that are at different stages of the collision process. Okay. So I'm removing my label so I can play this video of 2 galaxies. These are computer models of galaxies that look like frisbees. And as they come together, we stop the computer simulation. These are two real galaxies now. These are not computer simulation.
On mute.
We go back to the computer simulation of the two galaxies, and you can see their mutual gravity, the gravitational force, brings them closer together, and they start to intersect. When they're intersecting, we stop the computer simulation, change our perspective. So you can see they are actually intersecting. And here are two real galaxies that are in the process of intersecting. Okay, we go back to the computer simulation. Each galaxy stretches the other one out through a phenomenon called tidal force, same thing that causes tides to rise and fall in the ocean. And here are two real galaxies that are being tidally stretched. The main bodies of the galaxy start to fall together in this computer simulation. Time has been heavily sped up in the computer simulation. And right before the two main parts of the galaxies merge, we stop, change our perspective, and here is a real pair of galaxies going through the collision process. You've now seen 4 different real pairs of galaxies at different stages of the collision process. Now back to the computer simulation, the main bodies have merged. And again, we stop, change our perspective for one last time. And here is a real pair of galaxies going through a collision process. So the pairs of galaxies that I showed, real galaxies that I showed, they are different stages of the collision process, and the computer simulation was tailored to explain their appearance. Okay, so it's not a coincidence that they resemble each other, but the computer simulation resembles the universe. Here are 5 galaxies, Stefan's quintet, they're called. And a Hubble image on the left, HST stands for Hubble Space Telescope, an image taken in infrared light, near infrared light. In the middle is a James Webb telescope, again taken in near infrared light. That's what NIRCam stands for, near infrared camera. And on the far right is a James Webb image taken in mid infrared light. So MIRI, MIRI stands for mid infrared imager. And one of the spectacular things that you completely miss in the first 2 images is the fact that this top galaxy has this brilliant knot of light that only shines through in the mid-infrared, but not so in the near-infrared. Doesn't look particularly spectacular. This is the brightest thing in the mid-infrared image, is this spot. And you can see the 5 galaxies, the centers 1, 2, 3, 4, and 5. This one is not particularly nucleated, even though it has a nucleus in the mid-infrared, not very much. All right. Let me see. Moving on. I'm going to say a little bit about a discovery, a pair of discoveries that we made about the Andromeda Galaxy. By we, I mean my research collaborators and I. 2 discoveries. So in 2005, this is now 17 years ago, we discovered, to our horror, maybe not to our horror, to our amazement, that the Andromeda Galaxy, which you see as this little speck here, is 5 times bigger than people had previously thought. 5 times bigger. So imagine you wake up one day and you find your neighbor is 5 times bigger than you thought they were. That was in 2005. In 2012, 7 years later, 10 years ago now, a group that we were part of, was led by a team in Baltimore, made a second discovery, and that is the Andromeda Galaxy is headed straight for us. It's headed straight for us. So imagine this, you find that your neighbor is 5 times bigger than you thought they were, and they're coming straight for you. Okay, so both are bits of bad news, right? So this second discovery of the trajectory of motion of Andromeda led NASA to put out this little press release and a little movie that shows the future Milky Way and Andromeda galactic collision. If you thought galaxy collisions are cool, but they're not going to happen to us, you're wrong. It's going to happen to us. And Andromeda, I'm going to remove the label. Andromeda is this little speck here, 2.5 million light years away. And one of the sound bites that I love is astronomers wondered why Andromeda was getting bigger and bigger, and then it hit us. So here's a movie of Andromeda 2 billion years in the future, a lot bigger. And 3 to 4 billion years from now, there'll be a spectacular collision between Andromeda and the Milky Way. And when the dust has settled, quite literally, and everything has merged together in 5, 6, 7 billion years, there'll be one galaxy where there used to be two. Andromeda and the Milky Way will merge into a single galaxy. They'll merge into a galaxy that looks like an elliptical galaxy. The two black holes at the centers of the two galaxies will merge into one. And it'll look like an elliptical galaxy that's shown here. This is not, this is an existing elliptical galaxy that's the collision product of many, many Andromeda and Milky Way sized galaxies, not two. And if we, zoom into this, we'd see that there's sign of a black hole at the center. I'm not going to zoom in, but I'm going to show you a different kind of image of the black hole at the center of M87. This is the most photogenic black hole ever. This is an image taken pre-pandemic of the light bending around a black hole. The same galaxy that you saw in this picture, it's the black hole at the center of this galaxy, one of the monster black holes near us. It is bending radio waves from gas behind it because of the bending of space-time by gravity. Now, this is sort of Einstein's prediction. This is a radio image taken with a set of telescopes around the world. It's called, that combination of telescopes is called the Event Horizon Telescope. And in a real sense, it's the world's largest array of radio telescopes because it covers the whole world. This is another example of light bending, now through the lens of James Webb, to the mirror and lenses of James Webb. And you'll notice that there's a bunch of galaxies in the picture, and their collective gravity has highly distorted and bent the light of galaxies that are further away from us than these massive galaxies. Do you see these arcs, these giant arcs? Sorry, I know I'm talking to an arcs group, but now I'm not talking about achievement rewards for college scientists. I'm talking about literally arcs of light across the sky. In particular, look at this arc. It's a pair of arcs, this galaxy, and you see a faint line connecting them. What these arcs are the equivalent of the universe distorting the light of background galaxies. The mass of these foreground galaxies, their gravitational lensing has distorted the light of background galaxies. It's like picking up a mangled piece of glass and trying to read a newspaper through it. You won't be able to see the letters clearly. The letters will get stretched out into these arcs and other shapes. In fact, these are mirages. These two arcs belong to the same galaxy. So you can see that here. If you take a spectrum of this arc with the James Webb Telescope and a spectrum of this arc with the James Webb Telescope, what you get are these two spikes. This is produced by hydrogen. This is produced by oxygen. But you can see that to within measurement error, they look like the wavelengths have been stretched out by exactly the same amount for the upper arc versus the lower arc. Notice that the hydrogen peak in the lower spectrum and the upper spectrum are at the same location. This is wavelength on the x-axis. In other words, these two images are of galaxies that are exactly the same distance from us, exactly the same properties, and that's because they are really mirages. They are pictures of the same galaxy that's been split into two by gravitational lensing. So James Webb allows us to see that. The other thing James Webb allows us to do is we can take the magnifying power of the gravitational lens produced by this galaxy, and we can put James Webb behind this cosmic telescope. Basically, this group of galaxies is acting like a telescope, a cosmic telescope, and James Webb can line up with that telescope and use that way we can look at the combined power of James Webb and a cosmic gravitational lensing telescope. And we can use this, James Webb has used this to see some of the most distant galaxies known to mankind, humankind. I love this image. This is the gravitationally lensed image that somebody has superposed on Vincent van Gogh's Starry, Starry Night. And I can't help thinking that Vincent would have been really proud of this superposition. All right. Now, I said that galaxies are important to us. We can see the ripples in the universe that produce galaxies. This is an actual map of the afterglow from the Big Bang. And little hotspots on this map give rise to infant galaxies, like you see in this, inside this red ellipse. These infant galaxies merge to produce big galaxies like Andromeda. Within it, there are stars. Some of these stars, every star is a chemical factory. It's producing through nuclear reactions, nuclear fusion reactions, and producing new elements in the periodic table, more and more heavy elements in the periodic table. And when some of these stars die, they explode, and this stardust spreads out through space. New stars are born from this stardust. You and I are made of stardust, and our sun and Earth is made up of this stardust. And because of that, we're able to harbor complex molecules like proteins and DNA, out of which wonderful life forms are formed. This is a picture of my son and daughter. My daughter's on the right, John Rockman. You might recognize Tara. My son is on the left, and he had just been adopted. And so living things, you, me, the COVID-19 virus, the wonderful blue whale, we're all produced out of stardust. We're produced from molecules, DNA and protein molecules that were actually, the atoms were created inside stars. And then when the stars died explosively, those atoms became available to our planet and sun. So we are products of stardust. This seems like a good point to end the science part of the conversation. And if I have another minute, I want to show you what we're doing with young people. How am I doing for time?
You're doing fine. Go ahead, Raja, please.
Thank you, Chris. Thank you. Okay. I want to say a little bit about people, right? Because even though astronomy is, you get to play with the coolest toys and you get to answer some of the biggest questions about the universe, what sticks with me are the people that I've felt some connection to. Here's Albert Einstein. We were talking about his theories. This is a photo taken in 1912. And on the right, the impressive facial hair is Einstein's collaborator, Carl Schwarzschild. Carl died very young, died during World War I. But Carl's son was born in 1912, same year that Einstein's relativity came out. Martin Schwarzschild went on to become an astronomer like his father, Carl. And of course, knew Einstein because after his father passed away tragically in World War I, after Martin's father passed away, Einstein would visit their home. Carl Schwarzschild was his closest collaborator. So Martin Schwarzschild remembers Einstein from when he was a child, from their days in Germany. Now, of course, both the Einstein family and the Schwarzschild family had to escape Germany because of what happened during the two wars. The rise of the Nazi Party in Germany caused them to flee Germany and come to the US. And Einstein and Martin Schwarzschild reconnected because they both ended up in Princeton. Einstein was at the Institute for Advanced Study, and Martin Schwarzschild was a professor at Princeton University, where he was one of my mentors when I went to graduate school there. So I have 1 degree of separation from Albert Einstein, thanks to Martin. And in Princeton, I met 3 other professors, Lyman Spitzer, John Wheeler. John Wheeler was Richard Feynman's PhD advisor, and Freeman Dyson, the famous Freeman Dyson, all of whom also knew Einstein, but they met Einstein in his later years when he came to Princeton, and they had met him at conferences. So I have 4, not 1, 4 1 degree of separations to Albert Einstein. Here's someone else I had the privilege of listening to in person in a talk, Stephen Hawking. He was pioneering work on black holes and radiation from black holes. And I'm highlighting these people because they were an inspiration to me. These 3 people were inspirations to me too. Vera Rubin is the discoverer of dark matter on galaxy scales. She was one of my mentors. One of my first research projects, I found myself competing with Vera. And instead of treating me as a competitor, she took me under her wing and gave me advice. And we worked on dark matter and galaxies through different lenses using different telescopes. The person in the middle is Subramaniam Chandrasekhar, a very, very famous astrophysicist who got the Nobel Prize. In fact, 2 of the 3 people in this picture got the Nobel Prize. All 3 people in this picture deserve the Nobel Prize. Vera should have gotten the Nobel Prize for her discovery of dark matter and galaxies. Chandrasekhar received the Nobel Prize well after the work was done. His work was initially snubbed. There was a certain element of racism in what he faced in England. It turns out that Chandrasekhar is my great-grand, not father, great-grand doctoral advisor. What I mean by this is one of my 2 doctoral advisors was Jim Gunn. Jim Gunn's doctoral advisor was Guido Munk. Guido Munk's doctoral advisor was Chandrasekhar. That's what I mean by great-grand doctoral advisor. And the person on the right needs no introduction. That's Mother Teresa. I had the great fortune of meeting her in person 37 years ago in August 1985. I remember those 30 seconds like they were yesterday. There were no words spoken, but in that moment, I saw what a physically frail and, a tiny, physically tiny person, what oversized impact a person like that could have on the world. Of course, Mother Teresa went on to win the Nobel Peace Prize and was, given sainthood by the Catholic Church. Inspired by these people and inspired by people in general, my team and I, Sierra, Anand, Amanda, and Christy, convinced me in May 2020. You all remember what happened in May 2020. There was a horrific murder of George Floyd at the hands of the police in Minneapolis. And we said, we're doing this work. We're doing this work to engage young people in science. Let's reposition our work and really let's think about how we can do this work in a way that's not tone deaf to what's going on in society around us. And we created this thing called CREST, which stands for Creating Equity in STEAM, Science, Technology, Engineering, Art, and Math. And I hope you can see that the letters CREST written out in this way form the crest of a wave, entirely appropriate for Santa Cruz, of course. But it's an umbrella program for many of the programs we were already running. We said, let's create some coherence. Let's really work on getting students from historically excluded groups, Native American students, Native Hawaiian, Native Alaskan students, students from Africa, students from India, Kosovo, Mexico, South America, involved in the research we do. So we're doing this through something called, we're really trying to create equity in STEM by encouraging young people to think critically in the context of research. So starting Sunday night, we'll be running a series of Shadow the Scientist session. So while we use the telescope in Hawaii, we are sharing our Zoom link with networks of students and educators around the world. We have signups from Botswana, Ghana, India, Mexico so far, and over the next couple of days, there'll be many more signups, I'm sure. And they'll all connect through Zoom. You're welcome to connect as well. So we do the Shadow the Scientist as a way of showing young people what science is like, what modern science is like. It's like dipping your toe in the water before you decide that the water temperature feels right or the people in the water seem like they're having fun. We need to provide this dip your toe in the water moment, and we do this through Shadow the Scientist. Once you decide that the water feels comfortable, we teach swim strokes. We teach Python programming. We teach R programming. We teach this in the context of research in astronomy or research in computational biology. And once you have done those things, you can take a deep dive, and we run a program called the Science Internship Program at UC Santa Cruz. We started with 3 students from the Harker School in San Jose. And this summer, there were 326 students, including 100 students from outside the US. Sorry, 100 students from outside California, including 66 from outside the US and 30 some in other states within the US. And there's a program led by Professor Annette Lee that I collaborate with her in this program. It's called We Are Stardust. So I can tell you more about these programs if you're interested. But after the plunge, after you take this deep dive, you can get involved in something called the Global Sphere Network. You can be an alumni buddy to other students. We want to track your trajectory of success. We involve teachers in the Science Internship Program. We have a peer-to-peer college and career counseling network, and we involve community college students in SIP. And with that, I will end my presentation and take your questions. And I'm happy to stop sharing my screen so I can see all of you wonderful people. Thank you.
That was such a beautiful presentation. Thank you, Raja. So interesting.
Thank you.
I'm sure there are questions, so people should just unmute if you have a question, and feel free to ask Raja whatever you'd like about any of what he presented from the astrophysics, astronomy area, or some of the programs that he's running too. I'm sure he'd love to entertain those questions.
Absolutely, anything at all. The more complicated the question, the less I'm able to answer it, the better, because it will get us thinking about things.
Raja, did you want to talk about your work, your art?
Oh, Nancy, I was going to have you show that at the last.
Okay. You tell
Let's
me
get-
when. I'm ready.
Well,
And
let's just see if we can get some questions first. Don't be
sure. I
shy.
mean, when you
Ellie looks like she has a question.
You know,
fantastic.
one
Yeah.
of the things that I mentioned yesterday at our general meeting was something that stood out about working with you is your mentorship of some of our ARC scholars across schools. And I loved that you ended your presentation on just talking about many of the people that influenced you and the people that you worked with. Just speaking to, I don't know, what do you think makes a good mentor-mentee relationship work in sciences?
Empathy, like any kind of human relationship, empathy is the key. Empathy and trust, of course. I think those are, putting yourself in the mindset of the other person. You have a lot to learn from them. They have a lot to learn from you. It's a give and take relationship. When you're a research mentor, have a research mentee. Amanda Quirk, my most recent ARCS awardee. I've learned so much from her, and about being a mentor, about being a researcher, just about being a human being, honestly. It's being open to I think being a good mentor requires one to be empathetic and trusting, to be honest, to be a lifelong learner, really, because you learn so much through mentoring. And it's very much about paying it forward. It's very much about, I've learned so much from these wonderful minds I've had the chance of intersecting with. And while I can't give anything back to them, I can give something to a younger generation. It's very much like parenting in that sense. You don't get to give to your parents what they gave to you, but you get to give that to the next generation. It's very, it's the scientific equivalent of of parenting.
Mm-hmm. That's great. Susan.
I would love to hear, Raja, you comment on the idea that you said the proteins, in fact, building blocks of our biological systems, arrived by explosions from intersecting galaxies rather than evolved on Earth from the interaction of elemental chemicals. So there are competing.
I want to be very clear. Of course, the molecules formed here on Earth, but the atoms that make up those molecules came from the explosion of other stars. The atoms themselves were not created on Earth. I'm talking about atoms like carbon, oxygen, nitrogen.
Yeah, the interelemental. So you weren't implying that the
molecules did,
molecules actually
not the molecules.
that far. Yeah.
It's the building blocks of the molecules, the atoms, because in the early universe, we only have hydrogen and helium. And it's only inside stars that the rest of the elements get cooked, lithium, beryllium, boron onwards. And the reason hydrogen and helium are not very effective to create big molecules, hydrogen can only form one bond. So it can be at the end of a chain, but it can't really be the central molecule with many tentacles going out, right? Hydrogen has one chemical bond to form. It has one electron. Helium has two. Helium could potentially be a central molecule, but helium is inert and it doesn't like to hold hands with anyone. So you really need to move up the periodic table to lithium, beryllium, boron. And, we call ourselves carbon-based life for a reason. Carbon plays an important role. So it's these atoms that are produced in the explosions of stars. And those, star formation is triggered by galactic collisions, but stellar explosions are at the front and center here of how these atoms got to the sun and the Earth.
And they're floating around as dust and have accumulated over time.
That's correct. They're part of the, those James Webb images of that thumb-like feature?
Yes.
Those are full of these elements. And it's when they condense under gravity that the central star has inherited those elements, and the disk of material that form planets have all inherited those materials from previous generations of now dead stars.
Thank you.
Thank you, Susan.
Nancy, do you have a question?
Yes. First of all, just an incredible presentation. So thank you so much. but I was wondering how you see the James Webb Telescope impacting not only your research, but your interest in your field. It certainly has caught, like I can't be at work without someone bringing this up and talk. I mean, I have a friend and he works at NASA, and I said, oh, it's cool to be at NASA again, right? It supersedes almost every conversation topic. So would love to get your insight on how you see this impacting everything.
I see two impacts, Nancy. That's a great question, and thank you for your kind words. So, two impacts. One is it's a technological feat, right? It was the perfect, in gymnastics, you land the perfect 10. This was the 10.0 launch from, from the Ariane rocket in South America. What that did was, they were prepared to make corrections to the trajectory of the telescope to put it into exactly the right orbit. They had all this fuel they were carrying to make these corrections. You have to make corrections throughout the lifetime of the telescope. And the launch was so perfect that instead of having 5 years of fuel left, now they have 20 years of fuel left. They would have used that much up if the launch had not been perfect. It's an origami telescope, right? It went folded and opened. These are amazing technological feats. The sun shield is the size of a basketball court, and it was all folded up when it went there. This is the ultimate origami robot telescope. The technological feats, there were something like 350 points of failure where it could have just killed the mission. And these are technical hurdles that were overcome. And so I'm starting with that. That's a remarkable achievement. Collective human endeavor, not a single agency, not a single country, but really a global endeavor. The second thing, of course, is what this does is it opens up vistas of the universe that you've now seen in many images, in the same way that Hubble, the moon landing changed a generation and brought them into thinking about science, and the Sputnik generation or the Apollo generation here in the US. Hubble did something similar 30 years ago, where people who had no interest in science turned around and said, have you seen those images from Hubble? Same thing is happening with James Webb now, 30 years later. I think this, beyond discoveries made in the universe, it's the needed spark for human curiosity when our nation, when our globe is bogged down by so many other dire things like the COVID-19 virus, the war in Ukraine, the global warming. We need these sparks to see beyond our misery, to see that there's a reason to go on. There's a reason to continue to build technology. And the inspiration these missions provide really cannot be measured in words or dollars.
Thank you. Thank you for that.
Leslie, go ahead.
Oh, first of all, I want to echo Nancy's thank you for an incredible presentation for the layperson to understand on the science, and then to thank you for the work you're doing to create the pipeline for the scholars that we support when they get to graduate school. I just, it was so impressive on so many levels. But I want to talk about the part that's coming up, the art part, because the old thinking used to be that there was a right brain and a left brain. If you had one, you were sort of analytical and scientific, and if you had the other, you're artistic. I understand that that is breaking down, and you're a perfect example of that. And there must be some symmetry, something between the science and the art that maybe you could talk to us about.
Very much so. Leslie, again, thank you for your kindness. Leonardo da Vinci was my biggest role model when I was growing up, right? This is a person who was doing scientific discoveries, inventions, but he was producing beautiful art. The parallels I see go something like this. When I'm planning an experiment with James Webb or Keck or Hubble, you imagine something. You imagine something, you design an experiment, but how it turns out in the end is different from how you imagine it, because you have to respond to what the universe is telling you. What you're finding out about the universe creates some amount of uncertainty and divergence from the path you imagine, right? So, It's no different in art. If I'm imagining a beautiful image and I'm using a pencil to do this, how that pencil reacts to paper, or what impression of light and shade I'm able to produce, or how that paint hits canvas, is part of the problem solving, part of the reaction to, in this case, the medium. In the case of astronomy, it's reaction to our environment, the universe around us. So there's a problem solving aspect. There's a gap between the early, what you imagine early on, and what the final product is. Those are completely parallel between art and science. There's a creativity aspect to it. There's perseverance to it. There's hard work and faith that if you put in the hard work, something good will come out of it. And there's detail. When you see my art, you'll see there's a lot of detail. And in what you just saw in the universe, there's a lot of detail. Those are the parallels I see. I'm not a big believer in right versus left brain myself. I've heard the narrative, but I don't believe it.
I would agree with that. I think, does anybody else have a question? We're a little bit over time, and I don't want to cut anybody short, but people may have plans. Any other questions?
Raja, I have a question. It's Kay Corbell Metcalf. When you said that you took the 3,000 images of Andromeda, how long did it take to take 3,000 images?
4 years.
My God. So with that in mind, how long does it take to get an image on James Webb?
You know, it takes a matter of seconds. It takes a matter of seconds to minutes. The reason it took us 4 years is because we couldn't monopolize the Hubble Space Telescope for those 4 years. Other people were doing their stuff. So we got dribs and drabs of data. We're still getting them with Hubble. We're now imaging the other part of Hubble. And Kay, it's wonderful to see you here. Say hi to Preston from me. Kay is my connection in the art world, by the way, to the rest of the group here.
Well, then Kay will probably already have seen what we'd like to share now. So we just have a few samples of Raja's beautiful work. I've selected 5, and Nancy, if you could just bring that up quickly. And I also wanted to thank Nancy for putting our flyer together for tonight, our announcement. And I hope all of you at some point will try our Zodiac cocktail that Nancy put out there. I thought that was most fun and appropriate for this evening's session. So I'll let Nancy bring that up.
Should be an expert at the screen sharing stuff. We'll say, so, but wait a minute, I want to, one participant, okay. So now I want to go find it. I just go find it, right? Because I have it up.
I think so.
And of course, I have images of my art. If you need to resort to me screen sharing, I'm happy.
Want to go out? Want to go outside?
I wasn't sure how much time we had had.
Go see the tiger? No? You want lunch?
Can you see? Can you see? You can't see that.
No, not yet, Nancy.
I'm so sorry. You know, I'm trying to get it on, but it's just seeming not to want to. I did it beforehand.
Let me see what I can do on this side.
Okay, thank you. I did it. I tried it and it worked, but now it's not working.
Okay, well, I started with the Mother Teresa oil, and then I had the.
I know they're all there, but I just can't see it. If I do screen share.
No.
One second, I'll be right back. I've got it.
I could do it. I can do it if you want.
Yeah,
I've got it up.
You got it. Okay.
Tell me what images and I'll show them. This is my Mother
5.
Teresa.
Mother Teresa. Yeah, that's it.
So this is an oil painting on canvas, and this is inspired by my meeting with her in 1985. And, you know, the background is the polluted and congested city and pluralistic city of Calcutta. There's a mosque on the right here, and I don't know if you can see my cursor, but there's a mosque on the right and a church on the left. And she's looking into infinity. And, you know, this is the connection to astronomy. She is looking into infinity. Look at her gaze. She's not looking at anyone close. She's looking into the world, into the universe, really. This is, you know, she's the most famous person I'm ever likely to meet. You know, once you meet Mother Teresa, there's no topping that. I'm happy to show you, one of my favorite portraits is one of my mother. If I can show that, please, I'm going to display that. Is it okay to do that?
Yes.
Yes, yes.
And Raja,
please.
could you also show the one of your son? I picked that one, and then the mockingbird.
And the dog.
Well, that's who he called his son.
Oh yeah, my son. Actually, the one of the dog is is a different dog, not the
Oh,
one
is
that
it?
I,
Okay,
yeah.
because they look similar.
Yeah, they look very similar. That dog I had was when I was growing up, whereas the black and white one with my daughter is a more recent pup. So this is one of my mother. Okay, so my mother was an artist, and you could see that I've copied her art here. She did decorative
You're not
art.
sharing yet.
Oh, I'm sorry. I'm so sorry. Let me share my screen. Sorry about that. Okay, so here's my mom. You know, she wanted to be in the background of things, so she isn't sort of
Wow.
immersed in her art. So she did painting and decorative painting, and I took her decorative paintings and I copied them in pencil. And so what I've done is these two birds, these lovebirds in the upper right, the flower, this image of a goddess. This is the goddess's son, the elephant-headed Ganesha, this fish. But if you zoom in, I'm going to zoom in now.
Oh, come on over and look. Come on. Look.
If you zoom in, you'll see that I've used patterns, floral patterns that my mother used in her art to decorate her hair, her skin, her eyebrows, her spectacles, and everything is made up of patterns. It's just dark and light. Her hand is made entirely of patterns. I can zoom in even more so you can see the details of the patterns. So this is an image within an image. So at one level, it's just a set of patterns.
On her hands, it's like henna.
It's like henna, exactly. But her entire face, even the bifocals on her lens, everything is dark or light patterns.
That's incredible.
The folds of her.
That's incredible.
This is what I mean by detail, right? So there's a lot of detail.
So Nancy, you can go, Raja was in a show not too long ago at the Palo Alto Art League. He's a member there, and he does show his work there amongst other places like the Triton Museum.
I just had a piece in a show at the Triton that the show just ended. I'm going to show you the piece that was in the Triton. It was called Malcolm and Simon. You know, I love animals, so let me see if I can show you Malcolm and Simon. These are my student and her boyfriend. They have two cats, and you know, but this is all made up of words. If you look closely, the entire drawing is made up of, it's pen and ink. The whole thing is made up of words.
What's your favorite medium to work in? Is it pencil?
Pencil. It's pencil. It's pencil. You know, pen and ink. The trouble is, it can't be erased if I make a mistake.
Oh my God.
The whole thing is made up of words and contextual words. I was doing this in Europe. Emily, my student, whose picture you saw earlier, she was in Europe as well, and we were sharing pet pictures. And at one point, I said, "Okay, I'll do a portrait, except I'll use words from our Europe trip where I'm going to various places."
Oh my gosh, phone numbers. Oh my
phone
God.
numbers, yeah, phone numbers, and you know, a lot of meows written throughout. They're cats, after all.
Oh.
Yeah, this is full of words. The whole thing is, and it's sort of pointillism also, some dots, words. Yeah, there's some meows right there.
I see it, the last one. Oh, that's awesome. Oh.
But you know, you look at it from a distance and it just looks like an ordinary drawing, but it's got this layer.
Oh.
It has, well, it's not really Escher, but it has an Escher-like quality in that sense. You know, images within images.
Beautiful.
Okay, well, does anybody have anything else for Raja? I just want to say you are you're a man who's one of the most generous people with your time that I've ever met. And I'd like to just thank you again.
Thank you.
Yeah.
I'm going to close off with this one that I'm sharing. This is my daughter and her cousin. And this one is made up of words.
Oh.
The whole thing is made up of words, all of the shading.
You don't even see it.
You don't see it when you look at it from far, but when you come up close, you can see the words.
There it is. Oh, that's incredible, Raja.
Thank you. Thank you so much for indulging me. And
thank you.
The moment I start talking about my art, I can't stop, because that is the real me. That is who I really am, is an artist at heart. So thank you. Thank you for indulging me. Thank you for inviting me to do this. And I just loved every moment of it. Thank you.
Thank you.
Thank you, Raja.
Safe travels.
Thank you.
Yeah, I'll sign in for sure for Hawaii for that STS. And if anybody's interested, I'll send out the link. You
Yeah,
can-
send out the link
Send
and
it
we'll
to
post
the-
it out in the group.
Thank
The
you. Thank
entire
you.
group, Chris,
Yeah.
we're all interested.
Yes.
Thank
Okay,
you.
all right,
Yes.
I
So
will.
I'll see you on Zoom again in a few days, in a few
Yes.
nights. Yeah.
Yes,
Yeah,
that'd be
thank
fabulous.
you.
Thank you so
Awesome.
much.
Take care. Bye.
Bye.
Bye-bye. Great guy. He is a great guy.
He's such a nice guy. I mean, he's so